Welcome, everyone. You are joining us for Manufacturing Aware Design of Photonic Integrated Circuits. This webinar is presented by TechX and hosted by Photonics Media. Today, you're going to hear from John Cary, CTO and founder of TechX. He has a strong computational research and developmental background with more than 150 publications. He received his degrees at the University of California, Irvine, and Berkeley. So with nothing further from me, I'd like to welcome Dr. John Cary. Welcome.
Thanks, everyone, for joining. Let me share my talk here so that we can begin and I can start telling you about this. So what I'm going to talk about today is manufacturing-aware simulations of components in photonics integrated circuits. So the outline of the talk is going to be, there'll be some background to begin with. Then I want to introduce you to one of the things that manufacturing does, which is introduce roughness into the design, into the manufactured devices for photonics. I'll then talk a little bit about simulation methods in order to figure out how to predict those devices. Then I'll talk about some simulation directions and results. And finally, I'll talk about one of the big issues in such things for photonics is the need to get a large amount of resources for such computations. And we'll show how you can get the cloud and harness the cloud to do what you need to do for your designs. Silicon photonics, of course, it's a very maturing industry. And now it's accelerating even more rapidly because of the big explosion in artificial intelligence. Artificial intelligence needs large bandwidth, intense computational requirements. It needs power efficiency for profitability. There's all this discussion about increasing different ways of creating power because of the vast amounts of power that are being consumed by AI computations. So the one way to approach this is to use silicon photonics and bring it to bear on this problem. It has a bandwidth density, high bandwidth density, terabytes per millimeter. It has a lower power in terms of watts per system, better potential energy efficiency, and better potential cost in terms of gigabytes per second per dollar. So over on the right, you can see how silicon photonics and transceivers have been exploding over the years. And you can see how the percentage of silicon photonics and transceivers has grown to where it's now about 40%. And this is increasing the market dramatically. So photonics integrated circuits are interesting because one is doing photonics, but now one is using the manufacturing techniques that we have now for, 60 years of experience in the electronics industry. In electronic integrated circuits, of course, what we do is we have electrons that are carrying the information, and we now have sizes down to nanometers. Photonics is different in that the information is carried by photons, and the photon size, the sizes of the waveguides and such things are measured in microns. The other thing that's different about photonics integrated circuits compared to traditional electron circuits, is that the simulation actually for the photonics is more similar to analog circuits because time domain is important. And so you want to simulate the electromagnetic waves and how they interact with the structures. And this is not a digital simulation. It's not a circuit simulation. It's a full wave time domain simulation that you need. Over on the right is a cartoon of what such a circuit might look like with couplers and maybe a embedded photonic crystal, some optical waveguides, and a modulator, and so on and so forth. The simulation advances, the advances in silicon photonics now are going to depend on components. We don't really have a transistor in photonics. Here's a couple of quotes. I'll just mention the second one. Anthony Yu, the vice president of Silicon Photonics Product Management at Global Foundries, has said, "We continue to expand our photonics foundry capabilities to help our customers bring the advantages of photonics to different markets. We can be successful only if we apply the learning from our CMOS foundry model into photonics, along with close collaboration across various parts of the ecosystem to enable foundry-compatible, predictable model libraries and PDKs. So you can see every year there's a discussion at DesignCon or DAC on the photonics future. And one of the big problems now is there are deficiencies in some of our design simulations. They, in many cases, don't take into account back reflections or crosstalk, which impacts signal integrity. They're limited in some cases to single mode analysis. They don't have the substrate noise, and they're ideal geometries. And this is the big thing we want to talk about today. They're ideal geometries. They're not as fabbed in XYZ, including sidewall roughness. So the big picture here is that what we want to do is to decrease the time from a concept, an idea, a design, to the actual device. And we've seen this happen before in that we can take a design now, we can output the GDS of that design, we can send it to a fab, and we can have it built, and we can measure it, and then use that as input to our design to make the design more robust, and then give a new GDS and go to the fab and so on and so forth. And the problem is the iteration here. Every one of these iterations then is something that slows you down to getting your product out to the market. So the way this was improved was you take your design and instead of going straight to the fabricator, you simulate it. And the simulation then gives you information about how that design is working. And you can iterate this within your computation on your computer. And in doing that, you get to improve your design until finally you feel confident that your design is correct. And then you send your GDS to the design of experiment runs, i.e. the fab, and then you make sure that's working. And if there's something that needs to be corrected, you update your simulation capability, redo the design. Ultimately, when you're satisfied from your runs, you then send it to production. Now, early, we didn't have simulation. Where we are currently is the simulations are primarily extruded GDS. Okay, so GDS is the so-called CAD of EDA, I should say. So where we want to go is because photonics devices are sensitive to manufacturing variations, we instead want to take a design, create the simulation, do metrology on the fabricated device in order to understand what are the variations in the device, and take those two things and put them together and then simulate that. Then after you've gone around this several times, and this is very cheap because it's a computation inside of your own building, then send the result to the fab and hopefully get this big iteration loop of going from design to fabrication down to a fewer iterations. So the goal here is to bring metrology into the simulation to figure out what things are actually being created. And then you will get to fewer fab cycles with, for example, simulation of sidewall, line edge roughness, and various process iterations. So our goal is to equip the photonics integrated circuit design teams, perform rigorous fabrication, realistic simulations, and reduce the number of design of experiment runs, hopefully saving 1 to 3 iterations times 9 months, a year. So a couple of years in terms of time to market savings. That is the goal. So TechX, we're a small company, a small business in Boulder, Colorado. And what we've done is teamed up with various experts to address this issue. And our team consists naturally of ourselves, and what we do is code development and simulation. That's our expertise. We're collaborating with Dream USA. Dream Photonics is a company that is in British Columbia in Vancouver area. Lucas Krastowski is one of the principals. And we're partnering with them, and they're going to be providing the designs and sending them for fabrication under contract at multiple foundries. And then NIST, which is here, right here in Boulder, Colorado, the National Institute for Standards and Technology, will provide the measurements. This is important now, very important now for the U.S., because the U.S. has decided that it needs to get ahead of the game in terms of microelectronics and including photonics. And so there may be some chips involvement. And all of this is then putting things together for this vision. And so now what we're going to switch to for the rest of the talk is to say, what can we do now to reduce this uncertainty? So now I'm going to move and discuss roughness for a little bit. And roughness is well known in the community. Here's a nice paper, very nice paper from the Lipson group. And the first author is Roberts. And they did various analyses of roughness for realistic, fully 3D devices. There was the original work on this was in 94 by Payne and Lacey. And here's the citation up here. And the simulation usually proceeds by assuming a roughness model in which the height correlation function is given by some mean square height with some correlation length. Now, what they've done, what Roberts et al. Did, was to measure this using atomic force microscopy. And they also then, what Lacey, I should mention first, is that what Payne and Lacey did was they calculated, for example, loss due to roughness in a straight waveguide at a 2D system. And what Roberts did was then to calculate loss get the corrections for bending, such as in a ring resonator. And here's an example of one of their measurements of the roughness as you move along the surface. You can see that the roughness is primarily a variation along the direction, i.e. within the plane of the wafer, as opposed to across where it's more strongly correlated across. But in any case, this is a typical result where you have sort of 1 nanometer, half nanometer, 1 nanometer roughness mean square amplitude, and a correlation length that turns out about 90 nanometers or so. Now, there are other physical effects that we won't talk about today, but there's certainly sidewall slope. There can be variation in overall width on a longer scale, but we won't talk about those today. We're going to concentrate on roughness. Now, I'm going to move to simulation methods for analyzing such systems. When you analyze these systems, you have to do simulation. You can do a few things with analytically. Payne and Lacey did that for 2D straight waveguides. Roberts et al. Have a model for a curved waveguide, but in general, it's not analytically solvable. You have couplers. You have places where waveguides come together. You have splitters, places where waveguides split apart. And none of those things fit within what's easily done using analytic methods. And so therefore, we want to get at the effects of roughness on an array of such systems in order to understand the various things that I've mentioned before, namely optical back reflection, side scatter loss, matching modification, crosstalk, signal integrity. Now, for our studies, we use a tool that comes out of our company. It's called XM. It's going to be released in the next week or two. It's a finite difference time domain electromagnetic modeler. It's GPU capable, so it's very fast. It can get up to 5 gigacells per second, but it's also even faster because it can take advantage of multiple GPUs. But it's available for the desktop, cluster, and the cloud. There's no restriction that you have to use it in the cloud or in somebody's cloud. You can use it on your desktop just like other pieces of software, but you can also use it in, for example, a public cloud like Amazon's cloud. As I mentioned, it's capable of harnessing multiple GPUs, so it can solve really large problems and it can solve them faster. And that's an issue in photonics because in photonics, there are many wavelengths in the simulation, and that makes a problem what we call computationally large. Now, it imports GDS, STL, and STEP. This is GDS is what we're familiar with in this field. STL also is pretty familiar here. STEP is geometric CAD. It's what's used for modeling large systems. And it also has its own internal constructive solid geometry. And so it can do things like interlayer couplers, but I won't be able to show you that example today. It can add roughness. It can add a slope. For example, this is where we use the geometric CAD to go between surfaces. It has absorbing boundaries, subcell dielectrics, which give accuracy, conformal, perfect electric conductors, which is more of interest in the microwave arena. It can do the far field transformation, and so you can take the results coming off of your wafer and figure out what the pattern is some distance away. One of the things it has is variable grids, and this is something that's very important for reducing computation times. Here is a simulation of a straight waveguide, and this is a typical width of a waveguide with tiny roughness here at the edge. In this particular case, it's 2 nanometer RMS amplitude, and we model that by taking our cell width and having it to be a regular size that adequately resolves a typical mode inside of the waveguide if it weren't rough. And then near the edge, we make the cells very small so that you can see there are several cells across the roughness, and therefore getting that accurately simulated. So we do these simulations to provide, and we do them in time domain, because then we're able to get within a single simulation, we're able to get the loss across a spectrum of wavelengths in the system. The way we do that is we launch a mode coming in, and the mode is then Fourier analyzed, and you can get the power. Poynting's theorem says the power is the E cross B, the integral over the area. So this would be the time domain power, but you can compute the spectral density by taking the Fourier transforms of E and B and doing this cross product dotted into the normal of the plane and integrate that over the plane area. And that gives you the power as a function of omega. And so you can get the S parameter, which is the power out over the power in, over a whole range of frequencies, as I said, with a single simulation and Fourier transforms, and ultimately to get the result for the S param over a range of wavelengths. So what we've done here is an example of such a calculation. And this is the loss using a scan capability within the code. And we do a scan over the roughness of this waveguide edge. And we do that, and we get all the results for all the wavelengths for a given roughness. That is to say, we get this whole curve out of one simulation. So this is 1, 2, 3 simulations, and this is a simulation with no roughness. And you always do the simulation with no roughness because it tells you what are going to be the limits of your capability of simulation. Simulation can introduce losses itself due to numerical effects, and you want to make sure that those are not dominating what you are measuring in terms of what the actual loss is. So this errors at the edge of the band are indicated by where this turns down. And ultimately, then what you can do with this information is you can say, I need to get from A to B with a loss that's less than C. And here, this tells you then, by looking at this for the per wavelength, what do you need in terms of to get your roughness? If I need to be less than 20 dB per centimeter, at this wavelength, I need to have a roughness that's of order, say, 4 nanometers or less. Now, these are big numbers. The losses typically nowadays are smaller than that. All right, so now we want to go to something a little less trivial. So this is a Y splitter, and this Y splitter, the geometry was taken from the Roberts paper. And so what you see here on the left is what we call a strip splitter, or perhaps what they call a strip splitter. And that's one, and this graphic doesn't illustrate that, but this is a slight tilt of the simulation. And this is one in which the structures are raised. They're made of silicon, whereas the substrate is silicon dioxide. And the wave is ejected from the left and it comes down, and idiopatically, it gets down to the point where it can no longer propagate. And at the same time, because it's close to the outside waveguides, the wave gets transferred in part to the outgoing waveguides, and those increase the energy that they get. And as the pulse keeps moving down, it's forced out of the middle one and into the outer ones. Now, if you didn't do that perfectly, what would happen is you'd reflect some off of the ends and you would not have transmission of all your energy. Now, the rib splitter is the same geometry. We've used the same geometry. The difference is that you have the substrate of silicon dioxide, and then you have a layer of the silicon, and then the geometries are raised above that layer. So it's a little bit different in terms of the geometries being a little raised waveguide on top of a broad region. Now, before I show you the simulation results for these, I will mention that we did undertake a simulation of a splitter that was developed by Dream Photonics. It's proprietary, so I can't show you what it looks like. But these guys have designed something that has a very low insertion loss. And so the first thing you want to do to make sure that you can measure their loss due to the manufacturing variations is you want to see if you can get a very low insertion loss in the case where there's no roughness. So this is a simulation of the no roughness case of the Dream Photonics adiabatic splitter. And we have a loss in the simulation. This is a combination of numerical effects, reflections, various things that numerics causes. And you can see that we have, if it was a perfect splitter, it would be a 3.01 dB down because half of it goes in each leg or arm. And we have something that's less than 3.015. So less than 5 thousandths of a dB in terms of additional loss over what would be ideal, which would be the green line. Now they've measured their splitter, and indeed from their measured splitter, they see something that's down by 3.02, so 1/100th of a dB. And what we're saying here is if we can get the roughness, we know that if we have no roughness in our simulation, we can get a value that's lower than theirs. Now, we've seen other simulations that don't resolve it as well. And of course, they get a roughness they get a loss even in the no roughness simulation, which is much larger than what they're observing experimentally. And so you can't make a correlation between the experiment and the simulation, and therefore you can't figure out what's going on. So if we can get this to the point where we do see the agreement, then we'll know that we understand the loss mechanism and we can go on to predict other systems. Now, capturing these simulations requires a very fine grid. Here is a simulation on the left, the standard smooth splitter. Now we've improved these simulations over time so that we can do smaller roughnesses and we can do the simulation in a smaller overall size. But this simulation on the left is actually, there's something wrong here. But in any case, it ended up being 21.3 million cells. And we had to run it for 25,000 steps. And so that's a pretty big simulation. But we ran it on one GPU. It's a gamer quality GPU, an RTX 3070. And the simulation time was about 7 minutes. When we went to the much finer case, and we didn't go all the way to the finest case yet, we now have 105 million cells, and we had to simulate for 150,000 time steps. And now the simulation takes a couple of hours, doing it on a single gamer quality GPU. So this sort of simulation is well within the capabilities of the tool. And one thing you'll see here, you can't tell really here, but this is all for uh, uniform grid, and one can actually get savings by going to a variable grid, which we didn't do for this talk. So what can we learn already from such simulations? So we have simulated the smooth strip splitter and the rough strip splitter, and we simulated them for the rib splitter, in both cases as well. And we ended up getting some surprising, so a little bit funny results. First of all, I hadn't realized that the smooth strip splitter really did not have that good of a transmission. You could see that if you add the top port and the bottom port, you get to 0.35, only 35% transmission. In other words, 65% loss. Now, the reason for that is that the strip splitter has less coupling between the waveguides. And so there's less coupling out from the center to the side ones. And therefore, it doesn't couple as well going out. And so you get more loss. For the smooth rib splitter, you actually get very good coupling out. And now the transmission, if you add up these two numbers, it's 1 basically to the accuracy of the simulation. So for the smooth case, I'm getting very good results. For this large roughness case, now this is curious here. For the rough strip splitter, we got more out of the top port in this case, got a little bit less out of the bottom port. With the total that actually increased, we actually ended up getting more power out than we did for the case in which there was no roughness. Come back to that in a minute. For the rough strip splitter, that now it is no longer equally split. It's a 51%, 46, 7% split between the top and bottom port. This is a random effect because it's the roughness is a random variable that's within the simulation. But what's going on here? What we found by looking at the simulation in detail is that the mode that is launched for the strip splitter actually is still present in the center waveguide, even almost to the end. And that's because of the poor coupling, that it couples more poorly between the central and the outer waveguides. Whereas at the same distance, the rib splitter, you can see that nearly all the energy has been transferred out to the outer waveguides. But then you ask the question, why in the heck are you getting better transmissibility in the case of roughness? What we believe and what we think is happening here is that when you add roughness, you actually end up getting some scattering out of the center, not just the adiabatic transfer, not just the mode coupling transfer, but some scattering transfer that ends up, in this particular case, having given more energy forward than before. Now, this whole rib splitter idea is a double-edged sword. What you can see, here's the smooth strip splitter. Here's the mode, it's from our mode solver, and here's the smooth rib splitter. And this is what that mode looks like. And if you compare the strip to the rib, remember the rib splitter has a rib up here of silicon, and down below you have the same permittivity in terms of a whole layer of silicon, and therefore it tends to leak out here, effectively making it closer to the other rib splitter that's over here. So therefore you get more coupling. The other thing, which we don't quite understand yet, more simulations are needed, is here is where all the roughness occurs. This substrate is flat. It's all across. And so there's no roughness associated with it because there's no vertical walls. But over here, there is some roughness, but it's a double-edged sword here in the sense that we have this roughness and it looks like maybe the mode is staying away from that roughness. On the other hand, it's also the mode is leaking through the roughness. And so we don't really understand yet whether, at least from the computational point of view, we don't understand whether the roughness should have a smaller or greater effect. Okay. We are, however, seeing an effect. And in terms of, this is not really the right simulation to do because this says it's 4753, this is 4751. And so you would argue that this is more equal and therefore the roughness had a smaller effect, but it's not dramatically smaller yet, at least as observed in the simulations. We're not finished with this analysis, and we're going to continue doing that. Okay. So in the end, of course, more simulations are needed. All right. So where are we going? We're now working on a 1 nanometer simulation. We can keep it to about 900 million cells, say just short of 1 billion, and take a simulation that requires just over 400,000 steps by shortening the simulation, optimizing boundary conditions, judicious use of variable gridding, and we will end up with a simulation that's 900 million cells and 400,000 steps. But because we have the parallel GPU capability, we can throw 8 GPUs at this problem, and such a simulation is going to require about 3 hours of compute time. Unfortunately, we didn't quite get through the computing queue in time for this talk, but we expect to have that in a few days. And if you're interested in the results, come back and contact us. Okay, so now I'll talk about the cloud, because the problem that one has is how many people have 8 GPUs? A100s are expensive. NVIDIA A100s, and especially because of the AI explosion. The artificial intelligence explosion has simultaneously made a new set of markets for which photonics can go after, silicon photonics can go after. But at the same time, in terms of simulation, those are all competing for the same GPUs that we would like to use in order to do the computing and to predict how it will work. And A100s are, I don't know, about 10,000 a piece, maybe 8,000 now. And the new H100s, I don't even hazard a guess. We all know how NVIDIA's bottom line has gone way up. So we know they're significantly more expensive. And if you're a small business, you don't want to be investing, or you probably can't invest, let's say, a few $100,000 to create a parallel GPU cluster. And even worse, of course, that requires people to build it, to install it, and to maintain it. And so what one could do is go to the cloud for resources. And I'll be ready here in just a second, but just to give you an idea, you can go to the cloud and you can get, for example, an Amazon P316 large instance here, which has 8 NVIDIA V100 GPUs. They're not as powerful as the A100s, but they're pretty darn good. And you could compute on that. But now you have instead the difficulty of how difficult is it to work on the cloud, because it's not like falling off a log. And furthermore, so what we have done is made a general system where you can get on the cloud more easily and run our software. And by the way, I'll just mention that A100s and H100s are very hard to get on the cloud, but V100s are available. And something like this is about $17 an hour. And so if you had to do 3 hours, you might need more because they're B100s instead of A100s. It's about $50 for a simulation, according to these estimates. So what I'd now like to do is shift over to Joanna, because we have a pre-made video which shows how you can get on the cloud and do your simulations there to help you in your manufacturing design. Joanna, if you'd like to go ahead.
Hello, my name is John Sembauer, and today I will be giving a demonstration on how to use cloud compute to get XSIM running on an AWS workstation. From the Cloud Compute dashboard, I'm going to hit the New Compute System button up in the left. Next, from this menu, I'm going to select the software I'd like to use, the SSH key pair I'd like to use. I'm going to give my workstation a name, and I'm going to choose the storage capacity that I'd like mounted on it. Once I have those selected the way that I'd like, I can go ahead and choose my hardware. In the middle here, we have a bunch of AWS instances which are available to me, but since we're using XSIM, we want to use an instance that has GPUs available. So we're going to filter out all the ones that don't have GPUs available. Now we can see instances that have NVIDIA GPUs. And from this menu, we can see how many vCPU cores each instance has and how many GPUs each instance has. For a moderately sized problem, an instance such as the P3 8X large is a good choice since there's 16 physical cores on the node and 4 GPUs. I'm going to go ahead and select this hardware and hit Create Workstation. Once your workstation is created, your dashboard will look like this, where you'll find a Connect to Workstation button. You can hit this button to either connect directly in this tab, or you can hit this green arrow on the right side of the button to connect to the workstation in a new tab. This is what your screen will look like when you first connect to your workstation. Now that the compute system is ready, I need to get simulation files from my local computer up into the compute system. To do this, I'm going to use a free app called Cloudberry Explorer, which lets me drag and drop files and folders from my local compute system up into the Amazon S3 bucket. This is what Cloudberry Explorer looks like, where on the right is my local file system and on the left is my Amazon S3 bucket. I'm just going to simply drag and drop the folder that I'd like to upload into the S3 bucket. Now that everything's in the S3 bucket, I'm going to go back to the Cloud Compute dashboard to sync everything from the S3 bucket into the compute system. From this menu in the middle, you can see everything that's new since the last time you synced your compute system in S3 bucket. Once everything's synced from the S3 bucket to the compute system, I'm ready to start using XSIM. Now that the simulation files are on the compute system, I can go ahead and use XSIM as I would on any other workstation. From the Run tab, you can see things such as the time step, the number of time steps you're going to take, and the dump periodicity. In the Run mode window, I can choose the number of processes I'd like to use, as well as the GPU cards I'd like to use for acceleration. Since this is a 4 GPU workstation, I'm going to go ahead and select all the GPUs that are available. Once I've made sure that the time step and number of steps I want to run for is correct, I can go ahead and hit Run. Once your simulation is finished, you can head over to the Visualize tab to inspect the data. However, since these instances are expensive, a good practice is to shut this instance down and sync the data back to the S3 bucket and to start a new, cheaper workstation in order to do post-processing. To sync the data back to the S3 bucket for long-term storage, we head back to the Cloud Compute dashboard and resync the data as we did before, but in the opposite direction. Here you can see all the new files that have been created since the last time we synced the compute system in the S3 bucket. Once that you see that there are no changes between your compute system and S3 bucket, you are okay to shut down your instance without worrying about your data being lost. To delete your workstation, you simply move up here to the right and click Delete Workstation. Once this compute system is deleted, you're free to start up a new workstation with a much cheaper instance in order to do some post-processing of the data.
Okay, folks, so you've seen a video for how that's happened. I'll just add a couple of things to mention with regard to that video. Number one is, what John did was create a workstation. one can instead create a cluster and some number of nodes, each one of which has some multiple GPUs. So you can do your simulation on a large number of GPUs. And the cluster has the advantage that when the computing is done, it shuts down automatically and you are left on your visualization machine. And so you end up not having to shut down what you're not using. And another point is that although John showed about deleting the workstation in order to stop the charges, in fact, you can leave it configured and all you have to do is stop it. So there are a few more conveniences to working on this. So you've seen then how you can work on the cloud easily, configure your machine through a natural graphical user interface. You can connect to your workstation and you can be off to the races, computing and getting the answers you need for your design. Where I believe we are now is we now have the resolution and compute capability to incorporate manufacturing variations in simulations. That's going to give you an improved idea about how well a device will work before sending it for fabrication. With that, one hopes fewer design cycles and so faster to market. And what's making this feasible now are the parallel GPU runs that we now have capable within our software. And finally, of course, since not everybody has multiple GPUs, if you don't have the hardware work in the cloud, you can rent these things from Amazon, and we're all set up to help you do that. So I'd like to close by saying you can go to our website, www.txcorp.com, or you can contact, and I should have fixed this. This was supposed to say sales@txcorp.com. If you want to get information about how to get a copy of the code or how we can help you with your simulations, because we do things on both a consulting basis and we do things in terms of software sales, we can do either one with you and help you get this working on the cloud. So with that, I will stop there and I'll take questions.
Thank you so much. Yes, everyone, we have time for a few questions before we close. So if you have not already, please go ahead and type your questions and comments into that webinar questions box. All right, so let's see. This first question I have here is, why do you use the AWS instead of Google Cloud or some other provider?
Our experience is that AWS is the best overall quality for users in terms of good tutorials and how to set up your account. In our cloud model, by the way, you need to go to AWS, create an account, and then you'll bring your account to us in terms of the cloud. Everything you have in terms of your hardware, your data, and everything belongs to you and exists on your resources. You don't have to give them to us for us to do the work for you. So if you're worried about privacy, that's important. And if you're really worried about privacy, we do in some cases work with AWS through their GovCloud, which is where the federal government uses now for classified simulations. So some of our customers like that as an additional benefit, and it gives you even more privacy and security if you're concerned about your IP leaking out.
Wonderful. Thank you so much. All right, let's see. This next person asked, do you model the change in dielectric due to an applied electric field from the change in electron density?
Oh, thank you. Very nice question. We're actually plasma physicists, and so we have a real good idea as to how electrons move around due to applied electric fields, even in condensed matter. And we are in the process now, that is on our roadmap, of coupling those two capabilities. And we have some new ideas for simplifying the workflow for these types of simulations. So what I would say for you is, please stay tuned. That is coming shortly.
Great. Thank you. All right. Let's see. This next person asked, how do you integrate with K-Layout or GDS Factory?
Good question. Very nice question. Our integration is fairly simple at this point. In other words, what we're doing right now is we're using these programs to output a GDS file that we then use as input. So our application engineers are very familiar with this workflow because they are so common in industry. So that integration is fairly straightforward. In the long run, our hope is to integrate GDS Factory, which is open source, into our workflow so that one can modify some parameters within our graphical user interface, create the new GDS, do the simulation, and see the results. So that's where we're going, but we are not there yet.
Wonderful. Thanks. All right, let's see. So this next question is, since fabrication variations like waveguide width variation are inevitable and lead to phase inconsistencies in large-scale PICs, is there a way to conduct simulation studies beforehand to mitigate these adverse effects?
I guess what I'd say is there's a way to do those simulation studies now, provided that you can supply somehow the GDS file that has the wavelength, the width variations. Now, in fact, GDS Factory can do that for you. So if you can do a modification, and by the way, our tool, I should mention, is scriptable, which is to say you don't have to run it through our GUI. You can run it on the command line. And so therefore, if we don't have the capability right now, and it's really important to you to get the capability now, you can write your own script in Python, for example, that modifies a parameter, modifies the GDS Factory launch to put the width variation in it, then sends that to our simulation software where it is where the results of that computed and the answers are given to you. Yes, we can do the width variations, but in a less, so to speak, shrink-wrapped workflow. But yes.
Great. Thank you so much. All right. This next person asked, is roughness important for only low power, high speed applications or for high power photonic applications as well?
I guess I would say that roughness is important for whenever you have an issue of scattering. If you're doing high power versus low power, you have to ask the question, are you still in the linear regime? And if you're in the linear regime, then it's the same. High power is the same as low power. And so therefore, yes, it's important for both if it's important for one. Nonlinear limit, that's a different kind of simulation problem. But I would say it's important for both.
Thank you. All right, this next person is asking about something that was on slide 17. They're asking, how is it possible to measure the splitter at such precision?
We spent a lot of time getting that precision, I will tell you that. 17, let me come back to 17. Yeah. And I must say that there always is a little competition between the experimentalists and the theorists, with people saying, oh, I bet you can't do this. But it's really critical when you do such a simulation to get your launching exactly right. Then you need to make sure that the mode that you're propagating in there has no errors due to the mode solver. You need to make sure that any energy that leaves your waveguide, let's say, because it's not exactly matched at the beginning, is absorbed when it gets to the edges of the simulation and doesn't come back. You need to make sure that as you approach the splitter, where now you first have those side waveguides in, you have to make sure that you have your initial point in your simulation far enough back that the reflections from that do not impact the answer for your simulation measurement. You have to make sure, I can go through this whole laundry list. I'm sure you don't want me to do that. It would take up the rest of our time. But I can just tell you that it is a long and detailed process to make sure that your simulation has none of these non-physical effects, or that you've taken into account all of these non-physical effects in order to get rid of artifacts and to get the right answer. It's a game of whack-a-mole.
Great. Thank you. All right, let's see. So this next person, they're actually asking about slide 6. They said, you mentioned metrology as an input into the simulation. Can you explain what inputs are included?
Let's see, I'm not sure I understand that question. I can say that you take the design, you take the GDS, you send it to the fabricator, the GDS comes back, you send it off to whoever's doing the measurements for you. In our case, it's going to be NIST here in Boulder. They do something like atomic force microscopy to tell you what the variations are. And if you really, and by the way, I should just mention here, let me give a plug. I really like this paper by Roberts et al. Yeah, and they've gone through the process in some detail where they use the atomic force microscopy, get the height as a function of position along the waveguide. So you have to get that. The difficulty is not so much that, which is to say you could take one device and put it in, do the metrology on it, get the waveguide, do the simulation, and then see whether you're getting the answer that you measure. That's a one-off. But for design, that's not going to work because you build one device and then you measure it and then you build the next device. And since it's a random process, the next device has different height variation as a function of position. And you can't measure every device you're going to build, right? So one of the aspects of this collaboration that we're undergoing is to come up with good ways of translating the metrology over a number of devices into an appropriate statistical model that can be then used to predict the performance of a device that you have not measured. So that's an important part of this. I'm not sure exactly what you're asking, but I hope that gives you an idea of what the answer is.
Great. Thank you so much. And I think we might have time for maybe one or two more questions. So this next one is, do you need to install your SW onto the client's cloud?
So the way it works, let me come back to here. Yeah. The way it works is that we have our software already on the cloud, such that when you go to our cloud, you come in through this GUI interface, but you have submitted something to us that tells us to build your cluster or workstation with your resources. And it's done through the Cognito interface, which means that we don't have any access to yours. We just are supplying the instructions so that you can end up with a correct hardware configuration that you want. And at the time that when you're ready now to go ahead and build this workstation, you build it with our software, and our software is downloaded then from a different area in the cloud at Amazon, and it is automatically installed into your cloud resources.
Wonderful. Thank you so much. And I think we have time for one final question. So this last one I'll ask is referencing slide 15. They said it was very interesting. Are there references that you might have come across that can be used to validate the accuracy of the roughness model?
We haven't gone through the search of the literature for that to validate this. So I would have to say that time ran out on this as we were preparing this talk, but that's one of the next things we're going to do. But thank you. And if you have an interest in that, please contact us and we'd be glad to work with. By the way, many of you probably are already doing such measurements. And if you would like to have somebody to work with you on helping you understand from a computational point of view, whether what you're seeing is what the getting more confirmation of your results, please contact us. We're open and willing to collaborate with people.
Wonderful. Thank you so much, John. And everyone, if you have not answered your questions already, please look out for a reply later. If you do think of another question, you're welcome to reach out to us at webinar@photonics.com. That's webinar@photonics.com. And just a final note, the whole session was recorded. It will be available on the Photonics Media website shortly, but you will receive a link to that recording by email. So I'd like to thank everyone here for participating today, and I'd like to thank John Cary for presenting. That was wonderful. This webinar was presented by TechX Corporation and hosted by Photonics Media. So thank you and have a great day, everybody.